In the last video, we were discussing that the blue pulse generator here can be put in double pulse mode with a delay. So we can have it generate not one, but two pulses, pulse here and a pulse here, with a time delay between that we're free to set ourselves. And remember, at the moment, the pulse generator output on this cable is still connected to the LED, which is inside the detector housing near the scintillation plastic. So these are all fake events still, but we can just sort of see how the data throughput works here. So the LED flashes once, there's some delay that we can set, and it flashes again, and we can see that the whole detector apparatus is able to pick that up. We're interested in pulse pairs because we want to sort of let this run and see if a muon generates a pulse by stopping in the scintillator, and then another pulse sometime later by decaying in the scintillator as well. Then we know it must be a muon. So the question is, what sort of data processing do we do now to capture statistics on these stop and decay pulses that we get? Well, what we do is go to one of my personal favorite NIM devices in the whole bit here, and it's this one right here. And as you know, when I say NIM devices, there's amplifiers and SCAs and high voltage power supplies and counters and timers and all those things that you can slide into this NIM crate here. The time amplitude converter is one of my favorite. So the first thing is, let's just think about what it says here. TAC. It's the 566 TAC, and TAC stands for time to amplitude converter. So you got to think very carefully what this device does, a timed amplitude converter. So, as you might expect, if you want to start analyzing the time difference between two pairs of pulses here that may come from a muon decay, you're going to want to track the time delay between these two pulses here. So it could be that a muon stops and then instantly decays. So the pulses are going to be very close together. Or it could be that the muon stops and doesn't decay for a while. So the pulse will be further apart. So you see, you can expect sort of any range of the arrival of the second pulse relative to the first one, which is when the muon finally decides to decay. So you'll expect a distribution then of times on arrival to the detector. Sometimes the muon decay might promptly decay. Other times it might take a while, but there'll be a general lifetime in there. And as you might expect, it's probably most likely that the muon is going to decay soon, and maybe unlikely that it's going to sit for a really long time and then decay. Nonetheless, there will be a distribution of times between these pulse pairs, and that's what we want to measure. So going back to the TAC then, my favorite device of all the NIM equipment that we have here, a timed amplitude converter. So if you look very carefully at the TAC then, let me go down a little bit with the camera and zoom in here. You can see the way some of the BNC jacks are labeled. This one right here is labeled start. And you can just barely see it, but the one under it right here is labeled stop. So this is start, this is stop, and this is output. So these last three BNC lines are very critical to what it does here. So start, stop, and output. So think of it now on a device that's called a TAC, a time to amplitude converter. Why would it have a start, a stop, and an output? Timed amplitude converter. Well, here's what it does. It looks for a signal coming in on the start line, and if there's one, it starts a timing mechanism inside the device itself, usually charging a capacitor. And it allows this timing cycle to progress until it sees a signal on the stop line. And when it sees a signal on the stop line, it stops that timing process inside the time to amplitude converter. And what do you think comes out on the output then? So think like a physicist now. Suppose the start started a capacitor charging and the stop stopped it from charging. What do you think the output is? Well, how about the voltage on the capacitor? You'd probably agree then that the longer time between the start and the stop allowed the capacitor to acquire more charge, and the output then will be the voltage on the capacitor. Now, supposing you could linearize the whole thing so that the time between the start and the stop was always linear. So if the stop was twice as long as the previous start, the capacitor would get twice as much charge, although we know capacitor charging is non-linear, but suppose you could correct for all that kind of thing. Well, that's just what the time of the amplitude converter does. So let's go back up here to the oscilloscope and watch the time to amplitude converter in action. So I have the output of the time to amplitude converter hooked up to channel 2 on the oscilloscope here. So I'll go ahead and turn on channel 2 for you right here like this. There we go. And so you can see that when channel 2 is on, you can see this pulse coming out here, which is coming from the time of the amplitude converter. Now why it's all flashing and why we're not getting an event on every cycle of the pulse generator, I do not know, but this is the best I can get this going at the moment here. Now watch what happens. So what I'm going to do is I'm going to go back to the pulse generator. I'm going to vary the timing knob here between the double pulses and watch what happens to the output of the time to amplitude converter. So here we go. Watch the 2 pulses and watch the output of the time to the amplitude converter. So I'm going to make the pulses closer together. See the way the tach's output is smaller? And if I make them larger, see the way the tach's output gets larger and larger like that? Isn't that just the most beautiful thing you've seen? It really is a wonderful instrument. So I hope you can see then that on channel 2, what a tach does is it looks for timing between 2 pulses, and you can see them on the oscilloscope here, and it outputs a signal that's just proportional to the time between those 2 pulses. See? Very large delay between the pulses here, very large output on the tach. Very small time between the 2 pulses, very small output of the tach, and everything in between. So you see, you can go ahead and set your Muon detection system up, looking for these pulse pairs, and how about logging the voltage of the height of the pulse coming out of the tach? That voltage will be proportional to the time between the pulses, and so that way you can log all of those pulse pairs coming in, and that'll be your data set. Lastly, one of the settings on the tach also is how long should it wait. So you can see that there's 2 knobs here on the top. One is the range labeled in nanoseconds, and the other is a multiplier. So this sets the maximum range that the tach is going to wait for the end relative to the start before it'll internally stop and reset its own timing cycle. So this range here I have it set on 100 nanoseconds, which is too short for detecting muons with a lifetime of about 2.6 microseconds, but there's a multiplier down here which I have set on 100. So 100 nanoseconds times 100 is 10,000 nanoseconds, which is about 10 microseconds, so we're right on. So we'll have the tach looking for pulse pairs coming in that are somewhere between 0 and 10 nanoseconds separated in time.